We hear so much about these tiny machines, in our bodies called enzymes. But how do we actually measure and predict their activity? How do we go beyond just knowing that they're, important to really understanding how they work?
Well, that's where the field of enzyme kinetics comes in.
Okay.
It really dives into the speed of these reactions.
Mm-hmm.
It gives us this framework for quantifying their behavior.
Mm-hmm.
And it's not just theoretical either.
Right.
This knowledge has huge implications for things like drug development, understanding metabolic disorders.
Oh, wow. Okay. So we're talking about the speed at which these enzymes do their jobs. What are some of the key factors that come into play here?
Well, several factors can affect enzyme activity. You have things like the concentrations of the enzyme itself
Mm-hmm.
and the molecule it's acting on, the substrate. Then there are environmental factors like temperature and pH.
Okay.
But perhaps the most fascinating aspect is how the substrate concentration itself can really drive the whole process.
So more substrate means a faster reaction. Is
Yeah.
it that straightforward?
It's a bit more nuanced than that.
Okay.
To understand this relationship, we need to bring in the Michaelis-Menten equation.
Okay.
Now, before you worry about complicated formulas,
Yeah.
think of this equation as a way to predict how an enzyme will behave based on a few key ingredients.
A predictive model. That sounds useful. What are these ingredients we're talking about?
First, we have V, which represents the reaction rate, how fast the enzyme is producing its product.
Okay.
Then there's Vmax,
Uh-huh.
the enzyme's speed limit. It's like a car reaching its top speed. Even with more gas, it can't go any faster.
So even if there's a ton of substrate, the enzyme has a maximum speed it can work at. What else is in this equation?
That brings us to the substrate concentration itself,
Okay.
represented by S.
Gotcha.
This is the variable we can manipulate to see how it impacts the reaction rate. And finally, we have the Michaelis constant canomalum, which is really the heart of the matter.
Trum, that sounds like a crucial piece of the puzzle. What
Yeah.
exactly does it tell us?
Think of Kmam as a measure of the enzyme's affinity for its substrate.
Go ahead.
A low Kmam indicates a strong attraction. The enzyme works very efficiently, even at low substrate concentrations.
Uh-huh.
Conversely, a high Kmam means the enzyme is less efficient, requiring a higher concentration of substrate to reach, a decent speed.
So Karemim helps us understand how much substrate an enzyme needs to really get going. Is there a
Yeah.
way to visualize this relationship? It seems like it could get pretty complex.
Absolutely, and that's where the Michaelis-Menten curve comes in.
Okay.
If we plot the reaction rate against the substrate concentration, we get this beautiful curve that tells the whole story visually. So imagine a graph
Okay.
where the x-axis represents substrate concentration,
Okay.
and the axis shows the reaction rate.
Huh?
At low substrate concentrations, the rate increases gradually. But as we add more substrate, the rate climbs more steeply. The enzyme's becoming more active, converting substrate to product more rapidly.
So the curve starts off slow and then gets steeper. What happens as we keep adding more and more substrate?
Eventually, we reach a point where adding more substrate doesn't significantly increase the rate anymore.
Okay.
The curve starts to level off, approaching a plateau.
Mm-hmm.
Remember Vmax?
Yeah.
The enzyme's speed limit.
Right.
That's what's happening here. The enzyme is working as fast as it can, even with an excess of substrate.
That makes sense. So we have this curve that starts off slow, gets steep, and then levels off. Where does Kellerman fit into this visual representation?
That's the beauty of it. Kellum is visually represented on this curve.
Okay.
It corresponds to the substrate concentration where the reaction rate is exactly half of Vmax.
Okay.
So if you look at the curve,
Yeah.
find Vmax,
Uh-huh.
divide it by 2, and trace that point back down to the x-axis, that's your Kellerman value.
I see. I'm starting to see how powerful this curve is.
Yeah.
By looking at it, we can visually determine both Vmax and Kellerman. It gives us a real sense of how an enzyme behaves.
Precisely. It's a foundational tool in biochemistry. But to really dive into the complexity of enzyme behavior, we need to go beyond this basic model and consider things like enzyme inhibition.
Enzyme inhibition, is that like something preventing the enzyme from working properly?
Exactly. Inhibitors are molecules that can interfere with enzyme activity in a variety of ways.
Okay.
They're like tiny wrenches thrown into the machinery, disrupting the enzyme's ability to do its job.
So how do these inhibitors actually work? Are there different ways they can mess with the enzyme?
There are indeed.
Okay.
And we can categorize them based on how they interact with the enzyme.
Mm-hmm.
One common type is a competitive inhibitor. It directly competes with the substrate for binding to the enzyme's active site, the spot where the catalytic action happens.
It's like a game of musical chairs. Only one molecule can occupy that spot at a time. So if the inhibitor wins, the enzyme can't do its job.
Precisely. But the binding of a competitive inhibitor is often reversible, meaning it can detach and give the substrate a chance to bind, so it becomes a matter of concentration. If there's a lot more substrate than inhibitor, the substrate has a better chance of binding and keeping the reaction going.
That makes sense. But you mentioned other types of inhibitors. How do they differ from this competitive binding?
Another key type is the non-competitive inhibitor.
Okay.
This sneaky character doesn't compete for the active site. Instead, it binds to a different site on the enzyme, causing a change in the enzyme shape.
So instead of blocking the entrance, it's more like tampering with the machinery itself.
Exactly. This shape change can distort the active site, making it difficult or impossible for the substrate to bind properly. And unlike competitive inhibition, simply increasing the substrate concentration won't solve the problem.
Because the issue isn't about access to the active site anymore, but about the active site itself being distorted. That's fascinating. Are there any other ways these inhibitors can affect enzyme activity?
There's one more category worth mentioning, uncompetitive inhibitors.
Okay.
These are even more specialized. They only bind to the enzyme after the substrate is already bound, effectively trapping the enzyme-substrate complex and halting the reaction.
Wow, it's like a molecular trap. So we have these different types of inhibitors that can interfere with enzyme activity in very specific ways.
Yeah.
But why is understanding enzyme inhibition so important? What's the practical relevance of all this?
That's a great question. And it brings us to the real-world applications of enzyme kinetics. Enzyme inhibitors are incredibly powerful tools, especially in medicine and agriculture.
Oh, that's intriguing. Tell me more about how this knowledge is applied in those fields.
Well, for instance, many drugs we use are actually enzyme inhibitors.
Oh, wow.
They work by targeting specific enzymes involved in disease processes,
Yeah.
effectively shutting down or slowing down those processes.
So it's like targeted therapy at a molecular level. Can you give me a specific example?
Think about statins, a common class of drugs used to lower cholesterol levels.
Oh,
Statins work by inhibiting HMG-CoA reductase, a key enzyme involved in cholesterol synthesis. By blocking this enzyme, statins reduce the amount of cholesterol produced in the body.
it's amazing how we can use our understanding of enzyme kinetics to design drugs that so precisely target these molecular processes. Are there other examples of drugs working as enzyme inhibitors?
Absolutely. Many antiviral drugs work by inhibiting enzymes essential for viral replication. By blocking these enzymes, we can slow down or prevent a virus from spreading within the body.
So we're essentially using enzyme kinetics to outsmart viruses at their own game. What about applications outside of medicine? You mentioned agriculture earlier.
Right. In agriculture, enzyme inhibitors are often used as pesticides.
Okay.
By targeting enzymes crucial for the survival of certain insects or pests, we can control their populations without harming other organisms.
It's all about understanding the specific enzymes that are essential for the survival of the target organism.
Exactly. And that's why enzyme kinetics is such a powerful field. It allows us to understand these molecular interactions with incredible precision, leading to targeted and effective interventions in various fields.
This is truly mind-blowing. It's incredible how something as seemingly abstract as enzyme kinetics can have such profound and diverse applications in the real world.
It truly highlights the interconnectedness of the natural world and the power of scientific inquiry. But it's important to remember that even with all its power, the Michaelis-Menten model has limitations.
Oh, what kind of limitations are we talking about? Does it not always accurately reflect what's happening in real biological systems?
Well, for instance, the model is based on the steady-state assumption,
Okay.
which simplifies reality by assuming that the concentration of the enzyme-substrate complex remains constant over time. This might not always hold true in complex biological systems where things are constantly changing.
So it's a simplification that helps us make sense of things, but it doesn't always capture the full complexity of what's happening within our cells.
Exactly. Another limitation is that the basic model only considers reactions with a single substrate.
Okay.
Many enzymes actually juggle multiple substrates simultaneously, which requires more complex models to fully understand.
So it's like starting with a basic recipe, but then realizing that some dishes need more elaborate techniques and ingredients to truly shine.
That's a great analogy. And we also need to consider that the basic model doesn't account for things like enzyme inhibition, which, as we've just discussed, plays a huge role in how enzymes function in real biological systems.
So while the Michaelis-Menten model is a valuable starting point, it's important to keep in mind that it's a simplification of a much more complex reality.
Absolutely. It provides a foundation upon which we can build a deeper and more nuanced understanding of these incredible molecular machines.
This has been an eye-opening deep dive so far. We've gone from this seemingly simple equation to the complexities of enzyme inhibition and its real-world applications, and now we're starting to delve into the limitations of the model itself.
It's been my pleasure to explore these concepts with you. It's always exciting to share the wonders of enzyme kinetics.
We've covered a lot of ground. Perhaps it'd be helpful to summarize what we've learned so far before we dive into even more complex aspects of this field. Welcome back. Before the break, we were discussing some of the limitations of the Michaelis-Menten model, emphasizing that it's a simplification of a much more dynamic reality.
Exactly. And as we move beyond those simplifications, we enter the fascinating world of metabolic pathways, where multiple enzymes work together in intricate networks to carry out essential cellular processes.
Metabolic pathways, they sound a bit intimidating. Can you break down what they are and why they're so important?
Think of metabolic pathways as carefully choreographed dances happening within our cells. Each step in the dance represents a chemical reaction, and enzymes act as the lead dancers, guiding each step and ensuring the smooth flow of the entire performance.
So it's like a cellular ballet with enzymes leading the way.
Yeah.
But why are these pathways so crucial?
Well, these intricate dances are responsible for pretty much everything our cells do. Breaking down nutrients for energy-building complex molecules, detoxifying harmful substances, the list goes on. And without these pathways operating efficiently, our cells wouldn't be able to function properly.
So understanding how these metabolic pathways work is key to understanding how our cells operate at a fundamental level. But how does enzyme kinetics help us with that? Where do Km and Vmax fit into this picture?
Imagine each enzyme in a pathway as like a gatekeeper,
Okay.
controlling the flow of molecules through that pathway. The kinerum value of each enzyme determines how sensitive it is to changes in substrate concentration.
Okay.
An enzyme with a low kinerum is like a highly responsive gatekeeper, reacting quickly to even small changes in substrate levels. While an enzyme with a high kinerum needs a stronger signal to open the gate.
So the kinerum value is all about how readily an enzyme interacts with its substrate within the context of this pathway.
Exactly. And the sensitivity is crucial for regulating the overall flow of the pathway. If an enzyme is too sensitive, the pathway might overreact to small fluctuations, leading to an imbalance.
Right.
But if it's not sensitive enough, the pathway might become sluggish and unresponsive to the cell's needs.
It's like finding the perfect balance.
I know.
Not too eager, not too lazy, just the right amount of responsiveness to keep the pathway running smoothly.
Precisely. And that's where Vmax comes in.
Okay.
It sets the upper limit on how fast a pathway can operate, just like a speed limit on a highway.
Gotcha.
Even if there's an abundance of substrate, the pathway can only go as fast as its slowest enzyme allows.
So COSM's about sensitivity and regulation, while Vmax sets the overall speed limit. But we've talked about individual enzymes so far. How do these pathways themselves get regulated? Is there a control system in place to ensure everything runs harmoniously?
Absolutely. Our cells need to be able to adjust the activity of metabolic pathways in response to changing conditions, both internal and external. If our pathways were always running at full speed regardless of our needs, it would be complete chaos.
That would be like constantly driving at 100-mile-per-hour regardless of traffic or road conditions. Not a recipe for success.
Exactly. That's where enzyme regulation comes in.
Okay.
Our cells have evolved intricate mechanisms to fine-tune enzyme activity and keep these pathways in check.
So what are some of these regulatory mechanisms? How do our cells keep these pathways in line?
One common mechanism is feedback inhibition.
Right.
Imagine a pathway where the end product actually inhibits an enzyme earlier in the pathway. It's like the final product saying, hey, we have enough of me now, slow down production.
It's like a self-regulating system ensuring that the cell doesn't waste resources producing more than it needs.
Precisely. Another mechanism is allosteric regulation, where a molecule binds to an enzyme at a site other than the active site, causing a change in the enzyme's shape and thus altering its activity.
So it's like having a remote control that can adjust the enzyme settings, either turning it up or down depending on the needs of the cell.
That's a great analogy. These allosteric regulators can be incredibly diverse, allowing for a fine-tuned response to a wide range of cellular signals.
This is all so incredibly complex. It's amazing to think that all of this is happening within us constantly ensuring our cells function properly.
It truly is a testament to the elegance and efficiency of biological systems. And through the lens of enzyme kinetics, we can begin to understand and appreciate the intricate mechanisms that make life possible.
This deep dive has taken us on quite a journey. We've explored the fundamentals of enzyme kinetics, delved into the complexities of metabolic pathways and their regulation, and even touched upon the limitations of our current models.
And what we've explored today is just the tip of the iceberg. There's still so much to discover and understand about these fascinating molecular machines.
It's both humbling and inspiring to realize that even something as seemingly simple as the speed of a reaction can reveal so much about the intricate workings of life itself.
Indeed. And as we continue to delve deeper into the world of enzyme kinetics, who knows what other wonders await us?
Well, on that note, it's time for us to wrap up this episode. We hope you've enjoyed our exploration of enzyme kinetics. Until next time, keep wondering and keep exploring the fascinating world of science.